Now we'll move into the next part of this webinar, that is the resonance of Kenichi's works. So we'll start with Professor Kari's talk. Professor Kari will talk about computational universality of reversible one-dimensional cellular automata. Uh, Sir, are you ready?
Yes, thank you, Kamalika. I'm ready.
Okay.
I'd like
Then
to
over
share my
to you.
screen.
Yes, please.
So do you see my screen now?
Yes.
Okay,
Yes, we can
thank
see.
you.
Thank you.
So first of all, I would like to thank our Indian colleagues for organizing this event in the to remember Kenichi Morita, who was such a special person to all of us. So I was really very, very sad and very surprised too when I heard about the passing away of Professor Morita. He was, of course, doing very much groundbreaking research. We all know in various reversible models like reversible cellular automata, counter machines, Turing machines, and in reversible computing in general. Now, I may be one of the few here who is old enough to remember how it started with reversible cellular automata. I mean, Morita's work on reversible cellular automata. I was a PhD student in 1989 when Morita solved a long-standing, well-known open problem by proving that a one-dimensional reversible cellular automaton can be computationally universal. And in this paper, he also introduced his method of partitioning to guarantee reversibility. And this partitioning technique has been present in most of his works that came after this groundbreaking paper in 1989. So the organizers of this event said that I can have a technical talk. So I thought that what I would like to do is to review this construction by Morita and Harao, where they prove the universality of one-dimensional reversible cellular automaton. So you have to get into the mind setting in back 36 years ago. So today we of course know much more about reversible cellular automata than what was known back then. But still, I mean, quite a few things were known. So let me just review the basic things about reversible cellular automata that we certainly knew back in 89. So recall that the cellular automaton is called reversible if it is bijective on all it's bijective on the configuration space, and so the inverse function must also be a cellular automaton, must be defined by a local update rule. And here we are talking about cellular automata on infinite grids, not in finite cases like periodic boundary conditions or constant boundary conditions. By a simple compactness argument, in fact, we know that bijectivity is enough. This first condition of bijectivity directly implies that the inverse function is also a cellular automaton. But the inverse cellular automaton may have much, much larger neighborhood than in the forward direction, but still local neighborhood. What was also known since the 1960s was that every injective cellular automata is bijective. So injectivity implies surjectivity. So it's enough to check that any two distinct configurations, they will have distinct images. In fact, we had two very different proofs of this fact. We have one proof that uses the Garden of Eden theorem from early 60s, which characterizes surjectivity of cellular automata in terms of so-called pre-injectivity property. They are equivalent. And pre-injectivity is a weaker version of injectivity. So injectivity clearly then implies surjectivity. There's a second proof that goes through periodic configurations. Namely, if a cellular automaton is injective, it has to be injective also when we restrict it to periodic configurations. I denote this restriction by GP. And on periodic configurations, because for a fixed period, you only have a finite number of configurations, injectivity and surjectivity are the same concept. And then again, by compactness from surjectivity on all periodic configurations for arbitrary large periods, you get surjectivity on infinity configurations as well. It turned out actually that to be very useful that we have these two totally different ways of proving that injectivity implies surjectivity, because nowadays when people talk about cellular automata on other kinds of grids rather than just a rectilinear ZD, you can define cellular automata on Cayley graphs of more general groups. It turns out sometimes you can use this first implication, like in amenable groups, and sometimes you can use this second chain of implications, like, for example, in residually finite groups. So that was very useful. But anyway, the main point here is that we knew already back then that every injective cellular automaton is reversible. What we also knew was that 2 and higher dimensional reversible cellular automata can be computationally universal. Already in 1977, Thomas Ottofoli showed how you can simulate any d-dimensional cellular automaton by d+1 dimensional reversible cellular automaton. So you can, by adding one extra dimension, you can gain reversibility. And now, because one-dimensional cellular automata, of course, exists, I mean, one-dimensional irreversible universal cellular automata, of course, exist, we directly get that there are two-dimensional universal reversible cellular automata. Maybe I will show this how we can use the extra dimension to guarantee reversibility that is not too different from the constructions by Kenichi, actually. So let's say that you have a one-dimensional cellular automaton F, which is known to be universal. Let's say over binary states at 0, 1, and let's say that state 0 is a quiescent state. So for example, you could take the elementary cellular automaton number 110, which was proved to be universal by Matthew Cook. And now I show how you can make a two-dimensional reversible cellular automaton that simulates this rule 110. So in our two-dimensional automaton, the vertical strips will be viewed as one-dimensional configurations, and they operate as one-dimensional cellular automaton. Now, here I show like a cross-section of these stripes. So we really have two binary layers. One layer is used as a history layer to store the information to make the thing reversible. Okay, and so here on the top track, over the higher track, we will simulate our rule 110. So by xi, I denote this infinite one-dimensional configuration on the top track, on a stripe number I, and yi is the binary sequence on the lower track in the column number I. And now this is what you do. You, on the upper track, you apply your rule 110. So F here denotes rule 110. So you just apply it on these vertical stripes, all of them. And you do the XOR operation to add to the top layer the lower layer. So the yi is XORed in the upper layer. And at the same time, you want to memorize what was this xi on the upper layer one time step before, so you store it in the lower layer. But you shift it by 1. So basically what you have here on column I plus 1, you store it in column I in the lower layer. And now this operation is reversible. I mean, this is an injective operation. If you want to go back in time, you want to know what was on the upper tracks one time step before, you can directly read it from the lower track, shift it to the right. So if you want to know what was xi, you have it directly available here. So you just copy it there. And once you know xi, and you know this xi prime, which is the new state in this column, you can compute yi, because it is just the XOR of f of xi and xi prime. So in order to go back in time, you actually apply the same rule 110 again, but then you XOR it with something different. So you get back one step back in time, and this is a reversible cellular automaton. And now if you initialize your system so that you put zeros everywhere except their initial configuration to rule 110, you place in one of the columns and you start iterating, what happens is that the cells to the right of this gray strip, they always remain in state 0, because 0 was the quiescent state of rule 110, and when you XOR 0 and 0, you get 0. So everything remains 0 in this yellow region. And so what happens on this gray region, that you just computed rule 110, you repeat, you get rule 110 twice, and again, you get rule 110 3 times. So truly, you are simulating on this one column rule 110. What happens on the left, you will get on the left all the history information that you need to guarantee reversibility, to tell you how you can go back in time. So you get some sort of a garbage or random looking stuff on the left, but it's really not garbage, it's your history information needed to go back in time. So this was a really nice construction by Toffoli in 1977. But notice how it left open a crucial question. Do there exist reversible universal cellular automata in one dimension? Because this construction would not give you a one-dimensional reversible cellular automaton. You had the extra dimension that you needed to make the system reversible. And why was this difficult? Well, this was difficult because it's not so easy to construct reversible cellular automata in the normal formalism that we have for cellular automata. So normally we have local rules that get input from several neighbors, and then they output one value to the cell. And of course, these local rules cannot be reversible because there's more data coming in than there's coming out. And so it's not so easy to see from such a system in the standard formalism of cellular automaton whether the automaton is reversible or not. So there is an algorithm that we can run to test if a one-dimensional cellular automaton is reversible, but it is not obvious at all directly from the local rules whether the system is reversible or not, and therefore constructing reversible cellular automata was quite difficult. Now, Morita and Harao in their paper had the great idea of considering only particular types of cellular automata, namely partition cellular automata, where the reversibility of the system is really obvious. There, it's clear from the local rule that the system is reversible. So let me briefly remind you what is a partition CA. You can think of it in the following way. Your configurations have multiple layers, exactly as in the Toffoli construction that I showed you before. You had 2 layers. So here now you have any number of layers, and you update the cellular automaton in 2 stages that you alternate. In the first stage, you apply a bijection in every cell independently of the neighbor. So you apply a bijection on the state at every cell, and you don't need to look at the neighbors at all. But this kind of allows you to mix the different layers with each other. So for example, let's say I have 2 layers and 2 states, empty and a state with a token. And now let's say you might have such a permutation. So in each cell, you do this mapping independently of the other cells. And because this is a bijection, it's clearly reversible. You can go back by just applying the inverse bijection. Okay, this was stage 1. This stage alone is not very useful because information would not be able to propagate to neighboring cells. But then we have a second stage where you translate or shift the different layers independently of each other. So each layer is associated with a fixed amount of translation that you apply to that layer on the second stage. So for example, here we might say that the top layer we don't translate, so it has a shift amount 0, and the bottom layer let's say we shift it to the left. And so these 2 stages are alternated. On even steps you do a stage 1, on odd time steps you do stage 2. So let's say here, for example, we start with the stage 1 in this initial configuration. So you would apply the bijection. So you would map this into here. Then you do the second stage, you shift the lower layer. So the lower layer was shifted by 1. Then again, you apply in every cell the bijection. So you see that here you create 2 tokens, and here the token moves down like this. And then you shift, and then you permute, and you shift, and you permute, and you shift, and you permute, and so on. So already in this very simple example, you get rather complicated looking dynamics. So partitioning turned out to be a really great way to guarantee reversibility. And you can do this in any number of dimensions. In this example, I showed it in 1 dimension, but as we have seen in the wonderful constructions by Kenichi in his later works, you can do it in 2 dimensions, and you get really fancy evolutions of reversible cellular automata. Actually, this technique of partitioning is quite similar to an earlier technique by Norman Margolis, where you partition the grid, like here, let's say, into 2 by 2 blocks, and you apply a bijection inside each block, let's say inside the blue blocks. And then in the next time step, you change the partitioning, let's say, to the red one, and again you apply a permutation on the states in the red blocks, and then you alternate these 2. So you can see that there's a kind of similarity in these 2 methods. So Morita and Harao, in their 89 paper, used the partitioned 1-dimensional cellular automata to simulate a reversible Turing machine. So reversible Turing machine was known to be able to be computationally universal. So this was sufficient for universality. So just briefly to remind you that in a Turing machine, we have an infinite tape, and we have a finite state control that can access 1 cell of the tape at a time. And you have instructions here in the control unit that tells you that depending on the state where the unit is and the symbol in the cell that you are reading, the state can be changed and the machine can move on the tape 1 position left or right. So these are the operations of the Turing machine. Now, if you allow the Turing machine both write on the tape and move at the same time, reversibility becomes a little bit harder to verify from the Turing machine. So what Morita and Harao used in their paper is so-called quadruple formalism of Turing machines, where you are, in each time step, you are only allowed to either rewrite on the tape or move on the tape, but you are not allowed to do both at the same time. So the Turing machines now have instructions like that, which says that if you are in state Q and you are reading symbol A on the tape, you can change the state to P and you can rewrite A on the tape as B. And you stay in the same position, you don't move. So like, for example, here, let's say we have this situation and we have instruction like this. So you are in state Q, reading the red token, then you can go to state P and rewrite the simple green triangle. So you enter this configuration. So this is a rewrite step. And then you have also move instructions where you move regardless of what you have on the tape. If you are in state Q, this instruction would tell you that if you are in state Q, you can enter state P and move one position to the right. And this instruction tells you that if you are in state Q, you can enter state P and move one position to the left. So like here, again, in the same situation as before, if you have such an instruction, you can move to the left and change the state to P. The move instructions don't depend at all on what is written on the tape. And in the Turing machine, you have a set of instructions. That's the program of the Turing machine, and you can apply these instructions whenever they are applicable on your Turing machine configuration. In a non-deterministic Turing machine, you may have several instructions that you can apply simultaneously, but in a deterministic Turing machine, only one instruction can be applied in any situation. And it's easy to check in the quadruple formalism whether the Turing machine you have is deterministic or not. Well, here are the conditions written, but we don't need to worry about those details. It's very easy to check whether you only have one instructions applicable in every situation. Now, in the reversible Turing machines, you are also deterministic in the backward direction in time. And in the quadruple formalism of Turing machines, the inverse instructions can be easily constructed. So these are instructions that take you back in time. So if you have a forward instruction, which is a rewrite instruction like here, this would be the corresponding inverse instruction. So it takes you back. So here, if you in state Q, you replace letter A by B on the tape and went to state B, this does exactly the opposite. Now you are in state B and you have B on the tape, so you can retrace back in time. And similarly for the right moving instruction, the inverse instruction is the corresponding left moving. And for the left moving instruction, the corresponding inverse instruction is the right moving instruction. So it's very easy to find instructions that undoes what your forward instruction did. And so for the Turing machine program, you just, to get the inverse Turing machine, you just replace each instruction in the program by the inverse instruction. And then you have a Turing machine that exactly runs your system backwards in time. And if this backward Turing machine is reversible, then is deterministic, then we say that your Turing machine was reversible. You have a deterministic rule both forward in time and backward in time. And so this is what Morita and Harao did. So you take a reversible Turing machine M, and you can embed it into a partitioned one-dimensional cellular automaton with 4 tracks. You have 4 tracks. In the first 2 tracks, you write the Turing machine configuration. So you have on track 1, you have the Turing machine tape, and on track 2, you just write the Turing machine control unit. I mean, the state that you are in, you write it on this track in the correct position where the Turing machine is located. And then you have 2 tracks that are initially empty and that you just need to move your Turing machine left and right. So these 2 tracks are shifted left and right, whereas first two tracks don't move. So these lower tracks are like conveyor belts. So they continuously move left and right. And if the Turing machine wants to move one step to the left, you just move the state to the conveyor belt. It takes you one step to the left, and then you move it back up here. So they are used to allow you to make the moves. And so now you can directly tell what kind of local rules you should have in your partition CA corresponding to each instruction of your Turing machine. So if you have a rewrite instruction like that, in a Turing machine, in the cellular automaton, we would like to have in the bijection that you apply in all cells, mapping like that, because now you are replacing this configuration or this state in your configuration by that, which exactly simulates this Turing machine instruction. So let's say like here, this is our previous example. Now in the cellular automaton, you would have this instruction, which would tell you that in this configuration of the cellular automaton, you are just replacing in this column, you can replace it by this new column like that. So that exactly simulates your Turing machine step, rewrite step. Now, for left move instructions, we will use the conveyor belts. So we actually need two steps to do that. So for any left moving instruction like this, you will have in your cellular automaton these two instructions. So what you do is that you move your state to the conveyor belt, left moving conveyor belt, and you change the state to P. And then you need an instruction that just moves the state back from the conveyor belt to its correct location. Let's see the simulation. You have a Turing machine configuration, and then you have the cellular automaton local rules that correspond, were constructed for this instruction. So while the Turing machine shifts left in state P, here in the cellular automaton, we first, in the first stage, the PCA moves the state to this conveyor belt in P. Then we have, must remember, then we have the shift stage, the stage 2 of PCA. So the conveyor belt moves. And then we again apply the permutation, but we have exactly the correct permutation here to take P back to where it belongs. And then the conveyor belt moves, but the conveyor belt is now empty, so the movement doesn't cause anything. So we exactly simulated the step, moving step into two steps. And similarly for the right move instructions, you have a rule that takes your state to the right moving conveyor belt and then back from there. And finally, we need also instructions in our cellular automaton to all those cells where you don't have the Turing machine head. In those places, you don't do anything, of course, because the Turing machine tape is not changed in those positions. And with these rules, the PCA simulates exactly step by step. Well, not exactly step by step, but it simulates our Turing machine. Well, each rewrite instruction is simulated in one step, and each moving instruction is simulated in two steps. It's really an ingenious construction by Morita and Harao. There's one more little detail that we have to fill in. Notice that the local rule of the cellular automaton was only partially defined because there are many states in the cellular automaton that are not valid in any Turing machine simulation. For example, this kind of state you cannot have in a valid simulation. You cannot have two states. You don't have two Turing machine heads simultaneously. But that's not a problem because the reversibility of the Turing machine means that our partially defined local rule was injective. So we have this kind of illegal states equally many in the domain and in the range of our local rule. So these invalid cases, we can just arbitrarily map them in bijectively in our local rule. Doesn't matter how you map them because they are never used in a valid simulation. So we get the real bijection and a true one-dimensional partition cellular automaton that exactly simulates your reversible Turing machine. And it is therefore computationally universal if the Turing machine was universal. And this was Morita Harao construction. I'm sorry about being so technical, but I was told that I can give a technical description here. All right, so this partitioning technique really opened up new vistas for constructing small universal cellular automata, reversible cellular automata. And as we well know, Kenichi used this partitioning technique throughout his career after this 89 paper, and he got this very simple or small universal models, especially in higher dimensions than one. Already in 92, so this is just 3 years after the paper I was talking about, Kenichi proposed some universal partition cellular automata in 2 dimensions, where you just had 4 binary layers. He proposed 2 rules, which were also state conserving and also rotation invariant. So this is the paper. The first rule that he proposed was actually a reformulation of the billiard ball cellular automaton by Norman Margolis. The second one was different. So here is the local rule of the second one. You see we have like in this drawing, you see the 4 parts, 4 layers of the 4 neighbors in the von Neumann neighborhood. And you see how they are shifted, and then there's a bijection that maps them inside the cell. So these 2, you get from this layer a token, and from this layer on the north neighbor a token, and then you biject into this. And for example, in his book, you can find these fancy constructions. Here's used on that particular cellular automaton. So here is a implementation of Redkin gate in this particular partitioned cellular automaton with just 4 binary tracks. And so we have seen over the years how Kenichi was really a master of this kind of tremendous PCA constructions, and his books are really a source of inspiration on such construction, containing many wonderful PCAs. In this 2017 monograph on reversible computing, Kenichi has collected his constructions over the years into a book, which is really a wonderful book. Let me mention the following quote from the preface of the book. So Kenichi writes here that this book is not a comprehensive textbook on reversible computing, but describes mainly the results shown in the papers by myself and my colleagues, which were published between 1989 and 2017. That's really impressive. I mean, how many people can say such a thing about a book of 450 pages? So it really describes his work, and the amount of constructions is kind of staggering, I would say. Okay, this was just a table of content. Okay, so in this talk, I reviewed this Kenichi's classical paper from '89 that really started his work on reversible cellular automata. I would say it was a big thing back in '89. I remember I was a PhD student and I was so impressed by this work. And his ideas will continue to provide inspiration in coming years to us and, of course, many future generations. I just wanted to mention that as an example, just this month, Matthew Cook presented at the UCNC conference a paper titled "The Morita Gate is Universal." And in this paper, they solved an open problem that Kenichi proposed in 2012, so 13 years ago. So Matthew Cook and Ethan Palmier in this paper showed that one of the 24 possible reversible logical elements with memory, there are 24 such gates which have 2 input bits and 1 bit of memory. And it was known that 23 out of these 24 are not universal, but one of them was left open. While Kenichi Morita had shown that if you have 3 input bits, then pretty much all the gates are universal. But in a 2 input gate, it was not clear if there exists a universal one. And indeed, it turned out that one of these 24 gates was universal. And this particular gate, Matthew Cook and Ethan Palmier, they named the gate Morita Gate to honor these tremendous contributions by Kenichi. So I will stop here. Let me just say that Kenichi will be very much missed, but by all of us, by me also. I met him in several occasions in Automata conferences and basically Automata conferences, and he was always such a generous person. He will be greatly missed. So thank you for your attention.
Thank you, sir. Thank you so much for explaining in details the construction and also sharing your thoughts and memories. So I would like to ask the audience if you have any questions or comments, please. Yes. Yes.
Hi.
Yeah.
Nice to see you again, Jarko. Just one comment is that I think it's interesting that each field tends to have to reinvent, some of the concepts that they need in order to do their work. When I did the partitioning stuff that I did, I was completely unaware that, in the 70s, physicists already had lattice gases, which were exactly the kind of partitioning you're talking about in Morita's work. But there's too much information in the world, and people tend to have to reinvent things. Otherwise, they have to read everything. I just thought that's interesting. If you traced everything back, maybe it all has to go back to Archimedes or something, but we don't really know. Anyway, thank you for the talk. That was interesting. It seems to me that has a lot to do with the rules of what you're willing to call a cellular automaton. Many to one somehow, that format, which seems less, as a physicist, it's just locality and crystal structure or something seems like the essential thing from the world, rather than a specific, very constrained definition. Essentially it can't obviously be partitioning, so you have to slip it in somehow. Anyway, just 2 comments. I'm going to talk about this stuff in a moment anyway, so I probably shouldn't have said anything.
Okay, thank you, Norm.
Thank you, Norm. Okay, any other questions or comments? Mr. Kari, you have also worked on reversibility for many years and did extraordinary solves and extraordinary problems and have a remarkable contribution. Do you have any impact of Kenichi's work on how you have looked about your way of looking at reversibility, or your thoughts or your research? Any impact of Kenichi's work has been there? Because you just mentioned that this open problem was solved when you were a PhD student. So you had just started your research career in that sense. So any impact was there?
Yes, in a way, yes. So there was also this open problem that I worked on, which was the question of how to turn reversible cellular automata when it's given in this formalism where you have multiple inputs and single output. Can you turn it into this partitioning? Can you make a partitioned cellular automata that would be the same? So that was a question I worked on quite a lot. Because I had proved that it's undecidable in 2 dimensions if a cellular automaton in this standard classical formalism, let's say, is reversible or not. So it was not obvious whether you can make a partitioned one. And I managed to do it in 1 dimension and 2 dimensions, and it was certainly inspired by Kenichi's work because he had shown that 1-dimensional partition cellular automata can be so powerful. So I was really curious to see if I can turn every reversible 1-dimensional cellular automaton into a partitioned one, and that turned out to be the case. By the way, the question, as far as I know, is still open in 3 dimensions. I was only able to do it in 2 dimensions. It was already getting so complicated. It would be nice to know if every 3-dimensional reversible cellular automaton can be converted into a partitioned one. But I don't know.
Thank you.
Along with this, Jarko, I have one question actually related to this one. See, a partitioning cellular automata as constructed by Kenichi is a little bit different. So, what is your opinion? I mean, from the classical sense and classical construction of cellular automata and the reversibility, how much it is different in the classical one?
Well, the formalism is very, very different because, as I said, in the classical one, the local rule is not reversible. It's just that somehow they collaborate the cells in such a way that you don't lose any information, even though if you look at a single cell, it seems as if you are sending out less information that you are getting in, but you have to do this kind of partitioning. I don't know any other way how to make the reversibility work except for this partitioning kind of thing. But I think we will hear from Norman about these partitioning techniques more. But indeed, the classical formalism is very different from the partitioned one, and but it seems that you really do need the partitioning in some form or the other to get reversibility.
Yeah. At a first look, it appears that it is a very engineering solution. If I want to construct a reversible CA, so how can I do from the local rule? It's a beautiful construction. It's a little bit engineering. As you mentioned in your talk also, if you use the amorous path, it is very difficult to get the reversible. If I want to get reversible CA, it's quite difficult. You have to check, etc. So it's an engineering way how to get a reversible CA from the rule.
Well, the engineering way, if you want to construct reversible CA, like Kenichi demonstrated, I think the partition technique is the right way to go.
Right. Yeah. Thank you for your talk.
But was it only the engineering reason that he introduced this partition CA? Or so, like we are listening from Kenichi's colleagues and students yesterday, it looks like there might be some other reasons also. Something behind the story. Why he introduced partition CA? Any comments on that from anyone? Maybe someone from Kenichi's students, anyone? Yes.
Yeah.
Imai is there. Professor Imai?
Monica, engineering word I have used, but in a close look when I read it first, this is not only engineering. Although I use the word engineering, this is not also engineering. How the neighbors are changing. Always a cell is partitioned. Within a cell is not a united element. That is, it has some components. I have thought in different way. Within a cell, some partition is there, and the partition's neighbors, they are also varying. It might have some resemblance with our nature and other things. As I read, first time when I read it, this partitioning, it happens like this one. But I said that I use the word engineering because if I want to construct a reversible CA, it's a very good idea. You just construct, you will get a reversible, injective function, and you'll get the reversible CA. That is guaranteed. So from that perspective, I said engineering.
No, I understand. Like maybe like Professor Imai was yesterday saying his background was in biophysical engineering. That is probably the
Yes. So he when he graduated to university, of course, unfortunately, or of course, the Department of Information Science does not exist. So I am not sure if he is a bit more younger. He might choose the course of information science, but anyway, at the moment, he decided to enter the Department of Biophysical Engineering. So anyway, engineering course, but quite a few staffs studying biophysics. So he has no idea of, in a sense, physics and computation related studies. And so the turning point is a professor who studies X-ray analysis, biophysicist, just asked to Kenichi, what or how is connection of computation and physical system or thermodynamics. So far they have no knowledge of previous work by Landau or Bennett or Toffoli or Fredkin. Of course, Norman. And so anyway, the beginning is just advice by the professor of biophysics. And he just noticed their works. So the beginning is, anyway, he one by one tried to answer or improve the result or open questions for each pioneering researchers. So, for example, in the case of Bennett, Turing machine, reversible Turing machine uses 3 tapes. So how to reduce the tape to 1, or of course, Toffoli or Norman's reversible cell automaton case, 2 or more dimensions is possible to be show they are universal, but 1-dimensional case is impossible. So then Kenichi tried to improve the result, and so on.
Thank you so much. Yes, so it might be as you were saying. So something from the, as he has studied something different which we have not studied. It's not the usual course of learning. So might be that was a one thing that has made him think in a different way. Yes. So Professor Kari, will you share any other personal memories of Kenichi's from the Automata conferences? Any particular memory of him?
Well, I remember his talks basically because I met him usually in Automata conferences, and I truly was amazed by his simulations, like everyone here said. So that truly amazed me. I didn't work directly with him. I mean, we don't have joint papers or anything, but because we both worked on reversible cellular automata as a topic, so I really made sure that I was always there when he was giving a talk. So I wanted to hear because he had so many great things to say. Yeah.
Thank you so much. So, anyone have any other questions for Professor Kari or Professor Nimai? Otherwise, let us listen to a part of his talk and simulations. Yes. Subroto, can you please play a part of his talk that he has given us on reversible Turing machine and some I think parity checker he built up with the reversible Turing machines. Maybe you can show that part.
Anyway, by giving a single glider, then computation will begin. Okay. But it takes very much time. Therefore, we use hyper speed mode. But if we use such mode, glider flies very fast, but therefore we cannot see. Therefore, when it is accepted, then accept bomb will be hit, and explosion will occur. Okay? By such an explosion, we can see it is accepted or rejected. Okay? Now, we use a high-speed mode. It may be very hard to look at the time step, but here is a time. Generation is means the time. Okay. Now 4 million, 5 million, 7, 9, 12, 13, 14, 16, 18, 19, 23 million. Now we slow down. And look at how it will become, okay? Accepted or rejected. Please wait a moment. Flies here, okay? In this way, input 2 is accepted, okay?
So that was Kenichi. He created a bomb that will blast so that anyone can see that it is happening. Such unique personality.